Okay, in today's video we are going to go beyond what the book does with entropy. I want you to really understand what entropy is and what you can actually do with it, what people really do with entropy to some extent. Alright, the book gives you some ideas about, a feel for what entropy is and how to calculate it, but I want you to get a better intuition of what it really means and what it's useful for. So we're going to start with a simplified model, alright? Even an ideal gas is very complicated. It has lots of particles, it has lots of degrees of freedom, it can move in different directions, it occupies volume, right? We have to know, to give a microscopic description of our gas, we have to know how fast each particle is moving, what its internal energy states are, and so forth. So we're going to make a simplified system that we can apply thermodynamics to try and get a better feel. And so what I'm proposing is a simplified binary gas. So the idea is I'm just going to have a string of ones and zeros, all right? A binary number that will represent our atoms. If a digit has a zero, that means that the atom that digit represents is in a low energy state, and if it's a 1, it means it's in a higher energy state. All right, now when you think of quantum mechanics, quantized energy levels are a real thing, but our model is like super simplified. Our atoms can't move around, they can just have energy, and they can only be in one of two energy states. Now how many microstates does our system have? All right, so what is a microstate? It's any way I can realize, a string of ones and zeros. So if my system consisted of just one molecule or one digit, that digit can be either a 0 or a 1, which means there's two different microstates. If I have two molecules or two digits, I have 4 different possibilities. All right, so there's 4 different microstates for my system. With 3 different digits representing 3 different molecules, I have 8 different microstates. In general, I will have 2 to the n different microstates because a binary number with n digits can represent 2 to the n different numbers. All right? Now, that's the microstate. The macrostate we're going to consider is how many ones are there in my binary number. All right, so for example, up here, 0, 0, 0 has no ones. All right, so that microstate represents the macrostate of no ones. All right, the macrostate of having 1, 1. All right, there are 3 microstates that correspond to that: 0, 0, 1, 0, 1, 0, and 1, 0, 0. So those 3 microstates represent the macrostate of having 1, 1. Okay, what are the odds of a given macrostate? If I just generate a random string of ones and zeros, what are the odds that I get a certain number of ones? Well, let's think about this. The macrostate where I have no ones, they are all zeros, there's just one state. No matter how many digits I have, they all have to be 0. There's only one way I can get that. All right? Which means the probability of getting that state, if I just write down random ones and zeros, the probability I'll come up with all zeros is 1 microstate divided by the total number of microstates, which is 2 to the nth. Right? So there's 2 to the nth different numbers, binary numbers I could have written down. I want to know the odds of getting the one where it's all zeros, and that's just 1 out of 2 to the n. What are the odds that I write down a number that has exactly 1, 1? Well, it turns out that there are n microstates that represent that. Right? I have these n digits, and I can choose any one of them to be a 1. All right? So there's n different places I could put that 1. So there's n microstates that have just 1, 1. Therefore, the probability of writing down a number at random with n digits and a binary number which has exactly 1, 1 is n over 2 to the n. N possible microstates have 1, 1 out of a total of 2 to the nth possible microstates that represent all possible combinations. How about the probability of having 2 ones? Right? Well, here's how you can think about it. I go to choose which digit is going to be my first number 1, and I have n possibilities. Once I've chosen that one, I'm going to choose the next one, the second one, to be a number 1. I have n minus 1 possibilities because I've already got, that 1 I've already selected it to be a 1. I can't select it twice, so I have n minus 1 possibilities. So you might think that there's n times n minus 1 different microstates that have 2 number 1s in them. All right, but it turns out that we've overcounted. All right, because if I let particle 1 be a 1 for my first choice, and then my second choice is to make particle 2 a 1. That's the same microstate as me choosing that particle 2 should be a 1 for my first choice, and then for my second choice choosing particle 1 to be n. All right? So in both instances, I chose the first two particles to be 1s, but I counted that as two different microstates, and it's not two different microstates, it's the same microstate. So I have to divide that by 2. I've overcounted by a factor of 2. All right? And the probability then of getting 2 1s is just the number of microstates, so it's going to be n times n minus 1 divided by 2, and then that's all divided by 2 to the nth, the total number of possible microstates. All right? What about the probability of getting 3 1s? This is getting pedantic. We're almost done with this line of reasoning. Stay with me. All right, so the point is I have n choices for my first number 1, my first one, n minus 1 choices for my next one, and n minus 2 choices for the third one. Okay, but I've overcounted, right? Because, for example, the microstate where the first 3 molecules are 1s, I could have chosen the first molecule first, the second molecule second, and the third molecule third. Or I could have chosen the first molecule first, then chosen the third molecule second, and the second molecule third, and so forth. So it turns out that there are 6 different ways I could have chosen that same microstate, but it's all one microstate. 1, 2, and 3 are all 1s. All right? So I've overcounted by a factor of 6. The way you can think about that is there were 3 different ways I could have chose number 1, right? So my first one, for this particular microstate where the first 3 particles are 1s, I had 3 ways to choose which one was going to be the first one I picked, 2 ways to choose which one was the second one I picked, and then I had to choose the last one, all right? So 3 times 2 times 1 is how much I've overcounted. So the number of ways, the number of microstates that have 3 1s in them is just going to be n, n minus 1, n minus 2, and then I divide by my overcounting factor. All right? Now note that I can write this like this. N factorial is just the product of all numbers up to n. 1, 2, 3, 4, 5, 6, 7, right? And so forth. But I don't want the product of all of them. I only want n, n minus 1, n minus 2. So I'm going to divide by the factorial of n minus 3. So that'll divide out 1, 2, multiply by 1, multiply by 2, multiply by 3, multiply by 4, all the way up to multiply by n minus 3. So n factorial over n minus 3 factorial is the same thing here as this numerator. And then 3, 2, 1, that's just 3 factorial. All right? So there is the number of microstates that realize a macrostate in which 3 of my digits are 1s and the rest are 0s. Now, in general, if I try and find a macrostate of my binary gas here that has k 1s, the number of ways you can realize that, the number of microstates that correspond to that macrostate, is just n over n factorial over n minus k factorial times k factorial, right? So this thing right here is just multiplying by n, n minus 1, n minus 2, n minus 3. That's us saying, after I've chosen this particle, I have n minus 1 ways for the next one, and then n minus 2 for the next one, and so forth. And then this k factorial is the overcounting, correcting for our overcounting. All right? So there it is. So once again, I've scribbled over it, but the number of ways is just n factorial over n minus k factorial times k factorial. All right. So the probability, if I write down a random sequence of 1s and 0s of length n, the probability that k of them will be 1s and the rest be 0s is I just find the number of ways, w, as a function of k, and divide by the total number of microstates I can realize with the system. Okay, now let's do some statistics with this, now that we understand our system. So what is the probability of all of the energy in our gas being in the first half of the molecules? All right, so I've got this string of 1s and 0s. Well, those 1s and 0s represent molecules. 0 means low energy state, 1 means excited energy state, all right, extra energy. So I've got this energy, I put in, k units of energy, and that means k of my molecules are in the upper state. I have k number 1s in my binary number, all right? What are the odds that if I throw k units of energy in, that I just happen to get all of those number 1s in the first half of my binary digits, in the first half of my molecules. Well, let's think about this. The number of total microstates that represent the macrostate of having k number ones is just this equation here, right? We've seen this before. But inside those microstates of all possibilities where I have k ones are all of the microstates where all of the number ones are in the first half, right? Let's just look at those microstates. All right, so if I take half of my string, all right, and I say how many ways can I write the first half of my digits with k ones in it? And that's this value right here, right there. All right, so the point is this, all right, this is the number of ways I can write k ones in the first half. This is the number of ways I can write k in the entire string. So the probability I get in the first half is just going to be the ratio of those two. Okay? So here's a plot. So I plotted the ratio of these two numbers, and that gives me the probability that I will have all of my energy in the first and the left-hand side of my molecules, the first half of my binary digits, all right? And here is a plot as a function of k, right? So I calculate this for k equals 10, whatever. If I only have 1 unit of energy, my odds are pretty good of having them all in the first half of my molecules, right? That I have 1 unit of energy, there's a 50% chance it's in the first half, 50% chance it's in the second half. So with 1 unit of energy, the probability is 50%. But as I have more and more energy, the odds of having it all on one side drops dramatically. All right, to see how dramatically, I'm going to change this plot now to a logarithmic plot so you can see how fast it drops. And you see, after I get out to, if I have 1,000 particles and I put 100 units of energy in, I'm down to like 10 to the minus 32, 1 chance in 10 to the 32 that I will have all 100 energy units on the first 500 particles of my 1,000 particles. All right, so this is the idea of the thermodynamic limit. And the limit is you have lots of particles, probability becomes reality, right? And you're just going to say, what are the odds that all of my energy is in one side of my binary gas? The odds are essentially 0. Forget about it. Don't even worry yourself about it. It's not going to happen. All right, and that's what the thermodynamic limit is. Okay, so now let's use our toy model, our binary gas model, to try and understand thermal conductivity. All right, so consider 2 binary gases, each with n molecules. One has k units of energy and the other has j units of energy. All right, so how many microstates in my first gas realize that macrostate of k units of energy? All right, we've got that, right? So that's how many ways I can rearrange the energy among my n particles. All right, for the other gas, the second gas, I have a similar relationship, only now I have j units of energy instead of k, and this is the number of ways I can rearrange them. All right, now if I put these two gases in thermal contact, they can exchange energy. So the total energy is going to be the energy it takes to change 1 0 to a 1 times the number of 1s, right? So this is the total amount of energy that I have in my combined system. Some of it in gas 1, some of it in gas 2. All right, so I'm going to let R just be the sum of J and K. All right? Well, the probability that I have K units of energy on one side and the rest on the other, it's just the product of the two, of how well I can distribute K units of energy in this gas times how well I can redistribute what's left over in the other gas. All right, so this is the number of ways I can distribute K units of energy on my first gas, and this is the number of ways that I can distribute R minus K, so the total amount of energy minus how much was over here, into my second gas. All right, so the basic idea is I can have energy go back and forth, but assuming that I have so many units of energy in gas 1 and the rest in gas 2, all right, what's the probability that I get that much in one side versus the other? All right, and this should really, I've left off a factor of, all right, it's going to be not equal to that. It's going to be proportional to those two. All right, I have to divide this by the total number of ways I can redistribute energy over the whole thing. All right, but you can see this, right? So if I have the total number of ways I can distribute I can write ones and zeros such that I have K in one gas and the rest in the other gas. It's just how many ways I can arrange it in the first one times how many I can arrange it in the other one, right? It's multiplied because if I arrange it a certain way in gas 1, I have that, and then I have all the different ways I can arrange it in gas 2, right? So there's a whole bunch of probabilities. Now I change how I arrange it in gas 1, I have all those same probabilities in gas 2 again. So to get the total ways I can arrange all of the energy throughout the gas such that I have K on one side and J in the other gas on the other side is just going to be the product of those two. So let's plot that and see what it looks like. So here is a plot of the product of those two, W's, the ways I can arrange the energy in that gas, as a function of how much of the energy is in gas 1. All right? And what you can see is there is a peak at the point where I have half the energy in gas 1 and half in gas 2. All right? But this curve is not super narrow, so you might say, well, hey, look, there's some probability that I don't have exactly half the energy in one side or the other. And so you're going to get some statistical variance as energy just flows around randomly. Most often we're going to have about half of the energy in each gas, but there's some probability of having a little bit more in the first gas and some probability of having a little bit less in the first gas. But the probability drops quite a bit when we look at the probability of having none of the energy in the first half or all of the energy in the first half. All right, so 50% in one versus the other is the most probable, but there's some variation. Well, what happens is I increase the amount of energy I put in my gas. So instead of having 10 units of energy to split between the two, what if I have 100 units of energy? You see, going from 10 to 100, my distribution gets a lot narrower relative to my overall scale. All right? So what this is telling me is, as I have a bigger and bigger system with more and more energy, that peak gets narrower and narrower, and in the thermodynamic limit, where I have just lots and lots of particles and lots of energy to split among these particles, I am going to say, yeah, pretty much half the energy is in one side and half is in the other, and it's meaningless to think about any difference from that, right? Because you go very far from equal amounts in both sides, and the probability drops very down to almost nothing. All right? And why was this? Because there are many more ways to distribute the energy with equal amounts on either side than there are ways to distribute the energy if I have a lot on one side and less on the other side, in the other gas. All right? So you can kind of think that when I put two objects together, heat flows to maximize the number of ways I could realize that, say, to maximize the number of microstates that represent the macrostate of these two things being at the same temperature. If I have some heat flow from one to the other such that one side is at a higher temperature than the other, there are fewer microstates that describe that macrostate, so it is less probable. So we can think of heat flowing as just random stuff happening. The heat goes everywhere. There's nothing telling the heat that it has to go to the thing at lower temperature. It's just that there's so many more microstates that represent two objects at the same temperature than there are that represent one of the objects at a significantly different temperature than the other one. So we just never see that happening. It's just all of these microstates are equally possible, but there's so few of them that represent two objects at different temperatures compared to the vast number that represent two objects at about the same temperature that we just don't see that deviance very much. Okay, now why do we talk in terms of entropy more than talking in terms of the number of microstates that represent a macrostate? Well, the reason is, first of all, look at these numbers here. 2 times 10 to the 169th power. All right, this is just for a gas with 1,000 particles and 100 units of energy. You start to talk about the number of gas molecules in this room, all right, and all their degrees of freedom. Things get horribly big. There's lots and lots of different microstates to deal with. So entropy kind of helps with that by, first of all, multiplying by Boltzmann's constant, which in SI units is about 10 to the minus 23. All right, that helps a little. And then we take logarithms, and logarithms tend to take big numbers and make them smaller. So that's one reason to use entropy rather than the number of microstates that represent the particular macrostate. Another reason is that, remember, we said that kind of the total number of microstates for a combined system is the product of the W's for the two smaller systems. All right, by using logarithms, with entropy, instead of having to do a product, we can just sum them. So now entropy is not like something where it interacts with the other system. We can just say, this system has this much entropy, this system has this much entropy. Combined, the entropy of the total system is just the sum of the two, right? Because the number of ways you can redistribute things for the combined two goes as the product, but logarithms separate products into sums, all right? Right? Because remember, as you'll recall, the logarithm of A plus the logarithm of B is just the logarithm of A times B. Or sorry, A times B. Yeah. So logarithms take products and turn them into sums. So that is why we use entropy rather than the number of ways of distributing energy, or a number of microstates that realize a macrostate. Okay, so but if I take this same plot here where I had 1,000 particles and I said, how do I distribute 10 units of energy to one gas versus the other gas? Each gas has 1,000 particles in it. I got this plot. I can do that same plot, though, in terms of entropy rather than number. And you can see that high entropy is related to large numbers of microstates that realize that macrostate, which in turn means high entropy means high probability of that occurring. So entropy, why do things go to higher entropy? Well, because as my particles zip around in my gas, as heat flows around between two lead bricks or whatever, all these different random combinations are equally probable, all right? But the high entropy states have so many more microstates that describe that macrostate that they're just the thing that's just going to happen, and it's very unlikely that you'd see something else. Okay, so now we've talked about our binary gas model. Let's talk more in general about real stuff in real life, okay? When we talked about our binary gas, we said, look, the entropy of my total system when I combine two gases together was just the entropy of one plus the entropy of the other, all right? Now, if I let a little heat flow from one to the other, the change in entropy of the total system is just the change in entropy in one system plus the change in entropy of the other. And what we said was the system tries to maximize its entropy. So it exchanges heat back and forth, the entropy of one going down, the other one going up, to maximize the total entropy. And that is the most probable state. And that's what we're going to see in the thermodynamic limit, where we have lots of particles and fluctuations are negligible. All right? So imagine I move a little bit of heat dq from system 1 to system 2. All right? So the change in entropy of my system, right, as a function of dq is just ds dq. So this is my total system. What is the change in entropy for my total system? It's just the derivative. How much? So I took energy and I put it into system 2. So I have to add how much does the entropy of system 2 change, right, per unit of heat. Then I have to put in how much the entropy of system 1 changed when I put it in this little bit of heat. But I'm not putting a little bit of heat into system 1. I'm putting it into system 2. I'm taking heat out of system 1. So I'm going to put a negative sign here. So this derivative here represents how much the entropy of state 1 would change if I put some amount of heat dq into it. But I'm not putting dq into it. I'm taking it out of it, so I put a minus sign in front of it. All right? Now, I put some heat in. All right? So if I can take some heat from system 1 to 2, and this derivative is positive, that means that increases the entropy, and I'm going to do that. If that's negative, that means it decreases the entropy, and I'm not going to do that, and heat's actually going to flow the other way. When does heat stop flowing? When is the net heat flow 0? That's when putting heat one way or the other doesn't change anything. When this change is equal to 0, all right? So I reach equilibrium when these two derivatives turn out to be the same, all right? So the change in entropy with heat depends on the temperature of my system, all right? Depends on how much energy is in there. Once I get to the point where taking one little bit of heat from one and putting it into the other doesn't significantly change the entropy of either, then that's when I'm in equilibrium. All right, and these two cancel out. So you might suspect then that no heat flow happens when the derivative of entropy with respect to heat for my two systems is 0. Or sorry, not when they're 0, when the difference of them is 0, when they're the same. All right, but we also know that heat doesn't flow if temperature is the same. So this gives us a clue and tells us, two things have the same temperature when their derivatives of entropy with respect to heat coming into them are equal. And it turns out if you take an advanced course in thermodynamics, you will learn that you actually can define temperature to be 1 over the derivative of entropy with respect to energy flowing into the system. They usually use U rather than Q, all right? I'm not going to go into why. And this N and V just means you take the derivative assuming that the number of particles in the volume of the system is constant. Don't worry about that now, but just remember this basic idea that temperature is related to the derivative, how much entropy changes per unit of heat you put into the system, all right? Now notice I can take this equation right here and rearrange it, and then I'm going to take my du to the other side, and now I have ds is equal to du over t. That looks very familiar, I hope, because in our textbook we learned that the change in entropy for any system, an infinitesimal change in entropy, is just an infinitesimal amount of Q going into the system reversibly divided by temperature. So you can kind of see, where does this equation come from? It sort of comes from our definition of temperature, and our definition of temperature came from the fact that, you know, I'm going to reach a maximum of entropy when moving a little bit of heat from one to the other doesn't change anything. All right? Right? Maxima and minima are when derivatives are 0. All right? So when the derivatives of the entropy with respect to energy going into the system for my two systems is the same, I'm in equilibrium. So anyway, that's how I define my temperature. Okay, so now let's do something practical with this. So let's imagine I have gas in a big room, and I want to know what is the probability of finding all of the gas molecules in this room on the left side of the room. All right, so we said, look, in the limit, as we have large numbers of particles, deviations from kind of the norms, the averages, tend to get really small, and I can pretend like, look, gas is just always just going to be distributed equally through the room, and I don't have to worry about that. But let's actually calculate, what are the odds of finding just my gas molecules are flying around randomly. What are the odds of finding half of them in one side of the room at any given moment? All right? So there are various ways we could do this, but using our principles of thermodynamics, we can say, well, look, the probability is just going to be the ratio of how many microstates describe all of the particles in half of the room divided by all of the microstates. All right? So how do I find the number of microstates that describe the particles in half of the room, and how do I find the number of microstates total possible for all the gas molecules in my room? Well, we know that entropy is related to the number of microstates. So if I could find the entropy of a gas occupying half of my room and compare that to the entropy of a gas occupying the whole room, I could find the W's, right, the number of microstates, and I could do that division and get the probability. Unfortunately, everything we've done with ideal gases has been with entropy changes, not with absolute entropy. For example, we came up with a general formula that told us how the entropy changed when I did something to an ideal gas, and that's this formula right here. All right, but by combining these two equations, I can figure out what that probability is. So here's what I'm going to do. All right, I'm going to start with these two equations. All right, so the entropy of having my gas in half of the room versus entropy when my gas is allowed to fill the full room are going according to these two equations, all right? And then we've got our change in entropy equation, but let's assume, right, that we're not doing anything weird to the gas. We're just waiting to see when all the molecules happen to be in one side of the room. So we're not changing the temperature of the gas. We're not putting additional internal energy into it. So we're not going to change. So in the process of waiting for it to come and just show up in half of our room, the temperature is not going to change. So the entropy difference between my gas spread over the whole room versus gas in half of the room is just going to be NR, volume of half of my room, divided by volume of all of my room. So that's how much the entropy would be changed if suddenly my gas was all in one half of the room. All right? But that entropy change is just going to be my final entropy divided by my initial entropy, right? Which is that right there. K Boltzmann natural log, the number of ways of putting the gas in half of the room minus K Boltzmann natural log of the number of ways I can put the gas molecules anywhere in the room, right? The number of microstates that describe gas in the whole room, okay? So now I can use ideas of logarithms. First I'm going to take the K Boltzmann over to the other side just for kicks, all right? Now you look, all right? We've got one equation, two unknowns, but we don't really need to know both of them. We just need to know the ratio. And what happens when I subtract two logarithms? I can combine them into one logarithm, which is just the ratio. So I can rewrite this side as just a natural log of WH over WF. All right? That is the probability right there. That's the thing I'm looking for. Now, Another property of logarithms is if I multiply something out front, I can bring that in as the exponent onto the thing inside. All right, so now I've got this equation. All I have to do is exponentiate both sides to get rid of the logarithms. All right, so I have this is just equal to that. And of course, NR, we have our two versions of the ideal gas law, right? PV equals nRT. And then we have PV is equal to capital N, the number of molecules, K Boltzmann T, right? Little n is the number of moles, N is the number of molecules. So we know that NR is the same thing as capital N, K Boltzmann. So this just turns out to be 0.5 to the N. So the probability of just happening to look at some moment and saying, where are my gas molecules, and seeing that that they're all in one half of the room is just 0.5 to the N. That doesn't seem too large, does it? Well, let's calculate how big that is. I mean, that doesn't seem too small. It seems reasonable, right? Well, let's calculate what it is. So let's assume a room which is 10 meters wide, 10 meters long, and 3 meters tall. Let's assume that temperature is kind of room temperature, 300 Kelvin, and atmospheric pressure. If you go to the ideal gas law, you find that you have 7.3 times 10 to the 27 molecules in that room. So the probability that all of my molecules just at some moment happen to be in half of the room. I go and I say, look, what are the odds I'm going to see that? That's 0.5 to the 7.3 times 10 to the 27. I go onto my computer and I type that into Python, and it keeps lots of digits, and it gives me 0. All right? That's because my computer can't calculate anything smaller than. I tried this with increasing number of gas molecules, and I found that if I put in 0.5 to the 1075, I got 5 times 10 to the minus 324. That's the probability if I have 1075 gas molecules in my room of finding half of them, or finding all of them in half of the room at any given moment in time. That's with just 1075 molecules. If I go to 1076, the computer can't even calculate it, and it calls it 0. So you can imagine if I plug in 10 to the 27th, how incredibly unlikely that is. It's just not going to happen. Lifetime of the universe, you keep watching the gas molecules your entire life, it's never going to happen. All right.